The next session is going to be focused really on the impacts of conventional development, both to the site, but also have the cost impact associated with the way we currently develop, and then start digging into the different tools and techniques that we can use to really approach a site maybe a little more surgically and reduce the impacts of development, but also can reduce costs significantly. So some multiple benefits here. And I think we're all familiar with the current development. One way you can sort of sum it up is strip, cut, fill, and pound. And we strip, cut, fill, and pound for good reasons. I mean, people want to build buildings on solid footing. It can be, of course, easier to just clear an entire site. There can be good reasons for balancing a site, of course, using your cut for fill. So there are reasons that our conventional approach to development, but there's also, of course, some impacts. And you'll see on this slide on the lower left there, kind of the soil profile associated with that site. And in that top two layers there, really the O and A horizon in particular, and some B, we remove, along with the vegetation, a tremendous amount of storage capability for stormwater, as well as the other benefits. Of course, there are other benefits associated with the soils. But we lose a tremendous amount of storage capability, detention capability, flow attenuation. We have to work hard to bring that back. So we'll look at some ways that we can approach the site quite differently throughout this program. Compaction is something that we have to manage as best we can. Compaction is probably one of the most difficult impacts that we have to deal with when trying to manage stormwater on that site. And there's not a lot of research on this, but there is a bit. University of Missouri and Minnesota Extension, this graphic looking at the depth of compaction associated with different vehicles. The important message is, as your soil moisture increases on that site, your compaction increases. Compaction can go down quite deep, 2 feet and even deeper. And when you have deep compaction like that, and then you're trying to bring back some of that storage capability on that site, manage stormwater on that site, that is a significant impact. Compaction happens, it's more dramatic. Compaction can be deeper. If the soils are wet, we're often developing during wet season. So this is something we're going to work on, some techniques and ways to minimize that. This is a site from Tacoma, and as you can see, site completely cleared. And as we all know, with clearing large areas like this, there is associated management of the runoff from that site during construction, and that can be very expensive. During site development is probably the time where we have the largest impact to receiving waters. The picture here is a dramatic one. If an inspector walked onto that site today, I'm pretty sure that site would be shut down until, of course, things were brought in order. But that's a pretty dramatic example. But during construction, of course, there can be a lot of sediment moving off the site during all that site disturbance. So on the left there you see some numbers. There's been some research on the impacts of sediment to aquatic biota, and we know the impacts of sediment to stream, just physical impacts of stream, filling, stream gravel, impacting that habitat, losing pool, riffles, structural, the habitat of the stream that's important for supporting. Of course, in our case, we have endangered species listings in the area supporting salmonids, for example. This is a Midwest study found that suspended sediment levels of 50 to 80 milligrams per liter had significant impacts on stream biota. That's not a lot. Tom Schuler from Center for Watershed Protection reported a median TSS concentrations of about 4,000 milligrams per liter leaving construction sites with no temporary erosion sediment control, so that'd be probably a site like you see there in that picture. And then something like 280 milligrams per liter with temporary erosion sediment control. So big challenge. How can we develop a site and at the same time keep that those solids and TSS numbers down? And again, we'll talk about different techniques for doing that. Overall message, we're trying to approach the site more strategically, reduce that overall development envelope, and there may be, along with that, some phasing of the project. We're going to talk a little bit about the value of native soils and vegetation. Bottom line, so we know this from modeling we've done. We know from modeling that our native soils and vegetation are our most cost-effective and efficient stormwater management tools we have, by far. There's no BMP that can even come close to the cost effectiveness of our native soils and vegetation. how can we use that to our advantage? This was the first project for Pierce County to look at low impact development. It's a pilot project, went through the process on paper of redesigning that site using low impact development principles and practices. So this was quite a while ago. This was before really we had any actual on the ground projects in Puget Sound region. This was actually built. 24 acres, typical densities, extremely poor soils. In fact, this is a closed depression site. So even back then, under Pierce County Code, absolutely no water was allowed to run off that site. The first step is looking at site natural features, topography, soils, hydrology, vegetation, habitat, as well as other surrounding attributes, of course, zoning, and laying that out on a composite and coming up with this initial composite layout. You can see in the brown areas there, building area. Those are areas actually on that site that were already disturbed. In the green there, the open space, those are forested areas that were relatively undisturbed. There was a wetland on the property that had to be preserved. And then we also designed in some backup. That's what the wet pond is there. Low impact development's a new approach. Any jurisdiction is probably going to want some backup because they're not quite, they're not familiar with these practices and not sure how it's going to work. That was the overall layout, and you can see here we've reduced the development envelope significantly. And the idea here is also to use that open space for stormwater management as well as an amenity. This is the low impact development approach. Same number of lots, but of course smaller. Actually, these lots fall in line with what's very typical today. 4,000 square foot is not uncommon at all. Conserved about 15 acres in open space. And the idea here was to orient as many lots as possible to that open space, use it as an amenity, direct stormwater into those open spaces. Another big piece is the road layout, and we're going to talk about road layouts quite a bit today. And here is where we worked with Pierce County Fire and Safety, and at one point Pierce County Fire and Safety said, narrow the road. No, we will not go any narrower. We will not allow our roads to be any narrower. Our trucks are getting bigger. We have to bring 3 trucks out every time we respond, and we will fall on a sword over that. So we thought, okay. We actually went out on some drills with Pierce County, and they showed us how their, the size of their trucks and the equipment and how they responded to different events. And we came up with this loop design. And this is a road layout advantage for fire and safety. They loved it. They really liked this ingress and egress, 2 points in and out of an area. But also, that's a much easier layout to manage stormwater within. You can direct, so within those loops are bioretention areas, so you can easily direct water into those bioretention areas. So that was a drill where we learned a lot, and it was a win-win. Worked well for stormwater, and it worked well for fire and safety. And this is just an oblique of that. Maybe a little starry-eyed then. You can see the grassy pavers, the greenish tint to the road. That's pretty optimistic. I don't think we'd be doing that today, but at any rate, we were, we were optimistic back then. At any rate, you can see the loop configuration there, not only providing stormwater, not only providing good fire and safety access, but also an amenity that sort of provides a visual buffer between the homes. So really a great road design approach. Here's kind of the bottom line that I was talking about earlier. So as part of this project, then, we modeled the different low-impact development practices that we put in place. This is an older version of WWHM. This is a till-mantled site. It's in a closed depression, a glacial depression, so even back then there was no water allowed off of this site. Actually, this is back about 2000. You can see here on the chart, conventional development, detention storage required, 270,000 cubic feet. That's for the conventional project, the pond, basically, that's needed to store the water coming off that site. And then the low impact development, detention storage reduced. So we looked at, for each practice that we put in place, reducing the development envelope, bioretention, minimal excavation foundations, a little bit smaller road. How much did each of those things reduce that detention storage requirement? And you can see the numbers there. They're all beneficial. The thing helped somewhat, but by far and away was reducing the development envelope. So again, that conventional project that I showed you, that was what was actually developed there. They didn't have enough room on that site to create 270,000 cubic feet of detention. They actually had to purchase a separate site and ship the stormwater off to their site. This project built using a low impact development practice would have been not just a little, a lot cheaper. So when we ran some cost numbers on it as well, and it came out, the low impact development project came out much cheaper than conventional. As you can imagine, buying another piece of property just for stormwater was be quite expensive. The question is, how wide were actually all the roads were the same, then the loops and the main roads through the project. We had those at 20 foot. Thinking about the value of native soils and vegetation, how many people are familiar with BMP T530? So that's full dispersion. That's one of our BMPs that we've had in place for many years. And basically it says if you conserve 65% of your site in native soils and vegetation and you have 10% impervious area, you can direct that, the water from that impervious area out to that, disperse it out into your native soils and vegetation, and you are done with stormwater. That's it. Over. Essentially what you have is zero effective impervious surface, right? The idea is you have no water leaving the site. What you might not be aware of is there is a sliding dispersion scale. We asked the question to ecologists, well, what if somebody does a great job, they've got a difficult site, what if they do a great job of reducing the development envelope and they have 60% or 55%? Is it just 65 or nothing? And we came up with a sliding dispersion scale, and that sliding dispersion scale says, well, if you have 60 or 55% native soil vegetation, if you reduce the impervious area coverage accordingly in the same ratio, you can realize that same benefit if you disperse that impervious surface to the native soils and vegetation. So there is this sliding dispersion scale. This is one of our most effective tools. Difficult to use, of course, in an urban setting, right? I mean, you're going to be hard pressed to conserve a site in 65% native soils and vegetation. But it is one of our BMPs available, and I wanted to make sure that you know about that, because it's really at the heart of any of the BMPs that out there. This is BMP 530 is the one that really pertains most closely to this class. Now, this is a Kirkland bungalow project, very dense development, and the idea here in this slide is just to let you know that you can conserve native soils and vegetation even in very dense development, and in which they did here. Triad and Associates on this project protected, conserved native soils and vegetation even on a very tight site. So it is possible. Trees, we're going to talk about this more in depth at the end. Of course, it's the other part of the native soils, soils and vegetation. You saw from that initial graphic that our native vegetation does a tremendous job at intercepting and then evaporating a large part of our annual precipitation. And, well, it takes a village and fines to protect trees and soils. There's a lot to this. This is a picture from High Point in West Seattle, where they did a tremendous job at protecting some of their old heritage trees. Beautiful, the gorgeous old trees out there. But really, it takes contractor training, bonding and fines, signage. You can just see on that red oak below it, appraised value, about $28,000. And so they had arborists assess the value of the trees they wanted to protect there, put fencing around them, put up these signs, did some contractor training, and in fact, if any of those trees were damaged, you damage that tree, the contractor pays the city $28,000. That's an approach that worked very well on this site. Let's switch gears a little bit. We're kind of, again, taking kind of the 30,000 foot view right now, and we're going to zero in on each of these. Switch gears from the native soils and vegetation and talk about road networks. Key here is to understand that when we build road networks, from a stormwater and a receiving water, particularly for streams and wetlands, what we're doing is increasing the density of the drainage network. It's like we're creating a bunch of very fast-moving streams that are now moving downslope to our receiving waters, whether that be a stream, again, or wetland. From Schuler, again, local street right-of-ways can constitute over 25% of a typical urban watershed. It can be a very significant component. Streams and buffers constitute about 10% of a sample watershed. This was actually from the East Coast around Chesapeake Bay area, but this is kind of a universal truth. We increase our drainage network and the effectiveness of that drainage network to our receiving waters, and that has profound implications to the health of those receiving waters. There are lots of tools to reducing the road network while at the same time maintaining the effectiveness of those for transportation. This is just showing you a picture of a drill, really, an exercise at the City of Portland. This was looking at how do we take a dense road network and maintain the effectiveness of that for transportation, but reduce, in particular in this project, reduce stream crossing. Stream crossings of roads are particularly damaging, and we actually in this region have done some good research on that, of the impacts of roads and roads crossing streams in particular. How do you design strategically? This next section, I'll have to say is not particularly satisfying. There is no answer provided in this section. I want to start off just talking a little bit about scale. We are really focusing in, to a large degree, in this workshop, at kind of the development level. Of course, there are these other scales, all the way up to watershed, county, city, and region. This is a very important piece to keep in mind as we are thinking about site and development scale. We really need to think about the watershed scale, and we're starting to do more of that. Okay, so what are some of the things we have to think about along with the development scale? Okay, so take a watershed or subcatchment, watershed, that scale. We have a choice there, right? We can large lot development, 15,000 square foot lots, and that same watershed with a 5,000 square foot lot. Again, we've reduced the development envelope here. But that's not the only question. So you take for each separate watershed, subcatchment, whatever you might be looking at, do that in each separate watershed? Or does it make sense to move that development into one of those watersheds? There's no answers here. I'm not providing you answers. These are the questions that we need to ask. Are there very sensitive receiving waters in those watersheds that you might want to keep more pristine? Maybe they're drinking water sources. It would make a whole lot of sense to not be developing, because you're going to pay a lot of money down the road to try to mitigate the development impacts in a drinking water watershed. Lake Whatcom, poster child for the difficulties of allow development around your drinking water. Okay, but that's not the only thing we need to think about. Now let's project the road networks on top of those watersheds and looking at the 5,000 square foot lot in each watershed, as opposed to moving that development into particular subcatchments and the impact that might have on the road networks. Again, significant and dramatic changes in how we approach that. The best research we have on the impacts of urbanization on receiving waters is that site level, low impact development is necessary. Thinking about that, being more strategic, reducing the impacts at the site level, but it's not sufficient. Best science we have tells us that thinking at the watershed scale is necessary. That's not the subject of this workshop, but it's something certainly related. Now that we sort of wandered out into the regional planning scale, bringing us back down to the site level, you can apply this thinking also at the site. This is a project, a pilot project though, that was actually built in Pierce County. And do we think about that site, again, where we direct all the water to one centralized facility? That's been our conventional approach. Or do you break the site up into smaller sub-basins and manage the water in a more distributed fashion across that site? And that would be the approach we are going to talk about today, really the low impact development approach.